Okay. All right, so in the last lecture, we started looking at the advection diffusion equation. So the advection diffusion equation looks like this. We have a time derivative term. Well, I think I used the W as the unknown, plus advection velocity times the gradient of our unknown solution with respect to x. And we remember that this U determines how fast the solution is moving across the screen, right? So if it is, if this equation is describing the temperature distribution of a fluid, then U would be the velocity of the fluid. And this is also equal to kappa times the second order derivative of W with respect to space. And kappa is the rate of diffusion in the medium. All right, so we already looked at two of the limiting cases. The first limiting case is when our U is equal to 0. What we get is partial W partial T is equal to kappa times partial square W partial x squared. That is the heat equation. It describes the diffusion of something like temperature or density across a stationary medium. It's also a parabolic equation. And if you draw a diagram of x and t, what happens in this equation is if you change the solution anywhere by imposing a delta function on the right-hand side, the domain of influence is going to be the positive t direction. So this is called the domain of influence. Right, so this is for parabolic equations. We also looked at a second case. The second case we are looking at, we actually added a right-hand side, a known function f, being a function of t on the right-hand side. So that also can be accounted for in the parabolic equation. You can also add a f on the right-hand side. But the equation would only be non-trivial for the second case, because in the second case, in addition to U is equal to 0, we set the time derivative of everything being equal to 0. So looking at a stationary case. So when that is the case, we have kappa times second derivative of W plus F equal to 0. So there is no time anymore, right? So in this case, we get so-called elliptic equation. So strictly speaking, this is actually not a partial differential equation anymore, because my W is only a function of space x. So there is only one variable. In order actually to make it a partial differential equation, we actually have to, for example, look at two spatial dimensions. We also have a derivative to y. So in this case, we are looking at W as a function of x and y, right? And on this side, the diffusion which happens in the advection diffusion equation would actually work in both spatial dimensions. So this would really make it a partial differential equation. But for the simplicity of analysis, we first look at the case where there is only a single x and no y. The analysis would easily carry over to two spatial dimensions and even three spatial dimensions, right? So initially, we are just going to be looking at equation like that. So it's an elliptic equation in the sense that even if you have multiple spatial dimensions like x and y, so here, mathematically speaking, there is no difference if you denote the variable using t or denote the variable using y. I can easily have kappa times partial square w partial t square over here, right? But actually, the form of the equation makes a very significant difference. In the red equation, in the parabolic equation, the derivative to time is only first order, while in the elliptic equation, this additional variable I denote as y is taken derivative with respect to twice. We have a second derivative. And the effect is actually very significant in the behavior of the equation. So in this XY diagram, if you change the f, for example, at only a single point in the middle of the domain, how is the solution going to be changed? Is the solution still only going to be changed in the positive y direction? No, right? So the fact it is an elliptic equation makes it that if you change the solution here, if you change the right-hand side here, the solution is going to be changed everywhere in the entire domain. That's the characteristic of elliptic equation, right? So when you talk about what's the difference between parabolic and elliptic equation, that's the primary difference, is that a change in the right-hand side is going to affect not only in the positive t direction or a special direction in the independent variables. It's going to affect everywhere. So the domain of influence for elliptic equation is in the entire domain, no matter if you have one variable, two variables, three variables, or even more than three variables. Okay, now we get to our final, the last special case. So these are the two types of equations we are going to study. And for parabolic equations, it describes many kinds of diffusion problems. And elliptic equations describe a lot of equilibrium problems, like all the structural problems of looking at the loads on airplanes, the loads on buildings, the loads on bridges are described by elliptic problems, right? So if you look at a structure, look at a bridge, for example, if you put a truck on the bridge at one point, the stress and strain on the bridge is going to be changed everywhere, not just on the left of the truck or on front of the truck, right? So that's elliptic equations. And the final case also has a very wide range of applications, are hyperbolic equations.